Hi, I am Ijaz. In the today's lecture, we will discuss more about the convex and concave functions. We shall start by recalling some basic definitions about the convex function and some basic results that we have done earlier. So let's recall how we define a convex function. Recall a convex function. We have defined this convex function that if f is a function from an interval I into R, then we say that f is convex. Then f is convex if f of lambda x plus 1 minus lambda into y is less or equal to lambda times f of x plus 1 minus lambda times f of y for all x and y in the interval I and the point lambda belonging to the closed interval 0, 1. Now the significance of this lambda belonging to 0, 1 and this linear combination lambda x plus 1 minus lambda y, this linear combination, as we choose this lambda belonging to 0, 1, means that this lambda x plus 1 minus lambda y is a point in this interval I. So this way we have defined a convex function, and similarly if the inequality is such that f of lambda x plus 1 minus lambda into y is greater or equal to lambda f of x plus 1 minus lambda into f of y, then we call such a function as a concave function. Then we had taken up certain results regarding these convex functions. So one of the results was that if f from I into R is convex, if f from I into R is convex and x1 is less than x2 is less than x3, be any 3 points in the interval I, then such a convex function always satisfies f of x1 minus f of x2 divided by x1 minus x2 is less than or equal to f of x2 minus f of x3 divided by x2 minus x3. And similarly, we have done in our previous lecture that if f from I into R is convex, then, so in fact, we have done a necessary and sufficient condition for a function to be convex. We have defined it like this: a function f from I into R is convex if and only if the line segment, if and only if the line segment joining any 2 points on the graph of f of x, on the graph of f of x lies above the graph of f of x, lies above the graph of f of x. And we have already taken many examples of defining a given function to be convex by using this geometric property of the convex functions. So we will not repeat those examples again here, but we will proceed further. And the first new thing that we will define here is that we will define how we call a given set to be a convex set. So convex set. This is our first definition, which is new in this lecture. a subset E of the plane R square. A subset E of the plane R square is said to be convex. Is said to be convex if for every pair of points, if for every pair of points Z1 and Z2, Z1 and Z2 in E. So in fact, here we can see that since the subset E is contained in R square, so this Z1 and Z2 are the ordered pairs. If for any pair of points Z1 and Z2 in E, the line joining Z1 and Z2 lies entirely in E. Lies entirely in E. So if any subset of R square shares this property that a line segment joining any 2 points in that R square lies entirely in the same subset, then such a subset is said to be a convex set. For example, we can take a square, suppose x square plus y square is equal to a square, where a is any positive number, where a is any, in fact, a non-zero number. So we can take this a to be any non-zero number. A is not equal to 0. Then the graph of then this function is convex. Then graph is, so it's a square in R. It's a square in R square with radius equal to a and centered at origin. So we can take it like this. So therefore, this is the origin and this is the distance a. So this is the point A on x-axis, and in fact, this is a point minus A on x-axis. This is a point A on y-axis, and this is a point minus A on y-axis. Now here we can see that if we join any 2 points on this circle, then the line segment joining those 2 points will lie entirely inside the circle. So therefore, this is a convex set. And we can take, suppose, example number 2. The example of an ellipse. Suppose if we take the ellipse x squared by a square plus y squared by b square is equal to 1, then it is a convex set. Then it is convex. And similarly, suppose if we take few more examples, and we will take now some examples and we will just construct their graph. So suppose a function of this form. So suppose if we take a square, this square is also convex. Similarly, if we take a rhombus, if we take a figure like this is again convex, because if we join any 2 points inside this rhombus, then the line segment joining those 2 points will lie entirely inside the circle, inside this figure. And suppose now if we take a figure like this, if we have some function whose graph looks like this, then we can see that if we take a point here, then this function is not actually, this graph is not a convex set. This graph does not represent a convex set, because if we take, suppose, this point as Z1, and suppose if we take this point as Z2, then the line segment joining these 2 points will be like this. And we can see that this line segment joining these 2 points does not lie entirely inside this figure. So therefore, this is not a convex set. So therefore, this is not convex. And similarly, suppose if we take a function like this, then again this is not convex. And as we have earlier seen there, the square, this circle is convex, ellipse is convex. And similarly, suppose if we take a figure whose shape is, okay, now let's do not make any more examples. So this is clear that how we define a set to be convex set. So therefore, these are few examples of convex sets. Now to every function, we will associate a subset, and then using that set, we will show that how we can call a given function to be convex using the concept of a convex subset. Now with every function, f from I into R, we associate a subset of R square. We associate a subset of R square by defining the subset like E of f, and this is the set of points x, y belonging to R square such that f of x is less or equal to y. F of x is less or equal to y. Okay, so with every function we associate a subset of this form, then using this subset we can define a given function to be convex. Okay, so we have a theorem like this. A function f from I into R is convex. F into I R is convex if and only if and only if E of f is a convex subset of R square. Convex subset of R square. So this is a generalization, this is a characterization of convex functions using the concept of a convex set. So a function f from I into R is convex if and only if the subset E of R square associated to the function is a convex subset of R square. Okay, now let us do the proof. So as we have a necessary and sufficient condition, so we have to take two parts of the proof. We have to prove a necessary part as well as a sufficiency. So first assume that f is convex. Suppose f is convex. Then we need to show that the set E associated to f is a convex set. And using the definition of a convex set, we will show that a line segment joining any 2 points of E lies entirely inside E. So first let us choose, let Z1 be a point x1, y1, and Z2 be a point, suppose defined as x2, y2, be any 2 points of E of f, be any 2 points in E of f. Then we will show that the line segment joining these 2 points lies entirely inside E of f. And showing that a line segment joining 2 points lies entirely inside E of f, we need to show a condition something like this. We need to show there's something like f of x is less or equal to y. Okay, first let us define how we take an equation of a line segment joining 2 points z1 and z2 inside E of f. So for that thing, we will find out the looks of a point joining the line segment z1 and z2. So consider any point. Consider any point Z. Consider any point Z on the line segment joining Z1 and Z2. Then we have seen in one of the previous lectures that such a point Z has this form, then it is of the form. It is of the form Z is equal to lambda Z1 plus 1 minus lambda Z2. So in fact, this represents the equation of a line joining these 2 points Z1 and Z2 of E of f. Now here we can use the values of the Z1 as a point x1, y1. So this is something like lambda times x1, y1 plus 1 minus lambda x2, y2. Now using some simplification, we will get this to be something like lambda x1 plus 1 minus lambda x2, then plus lambda y1, sorry, this is comma here, lambda y1 plus 1 minus lambda y2. Okay, now in order to show that, now this is a line segment joining any 2 points of E of f. Now we will show that this line segment lies entirely in E of f. For that thing, we need to show a condition something like f of x is less or equal to y. So here we will show that f of lambda x1 plus 1 minus lambda x2 is less or equal to lambda y1 plus 1 minus lambda y2, proving that the set is convex. Okay, now let's call this interval. Now let the interval I be equal to the interval AB. So in fact, we have something like this now lambda x1 plus 1 minus lambda. And this is, as we already know, that lambda belongs to the interval 0, 1. So therefore, this lambda is here in the interval 0 to 1. So lambda x1 plus 1 minus lambda x2, it is a point inside the interval I. And we have now since the function f is convex, so we can write this f of lambda x1 plus 1 minus lambda x2. Now, by definition of convexity of f, this is less or equal to lambda times f of x1 plus 1 minus lambda f of x2. But now looking at these pointers, x1, y1, and x2, y2. Now, x1, y1 is a point in E of f, and this E of f is a subset associated to the function f, which satisfies the property that f of x is less or equal to y. Okay, but now since this point x1 is inside the interval I, and x1, y1 means that this y1 is the image of x1 under the function f. And similarly, when we look at this point x2, y2, y2 is the image of x2 under the function f. So therefore, this is equal to lambda times y1 plus 1 minus lambda times y2. So here we will put up the reason that because f is convex, and here the reason is because y1 is equal to f of x1 and y2 is equal to f of x2. So therefore, what we have shown, we have chosen a point. Actually, we had chosen 2 points z1 and z2 inside E of f, and this was the line segment joining these 2 points. Now it has this form, and now this point, we are now showing that this point lies inside E of f. This is a point of E of f, because we have shown that f of lambda x1 plus 1 minus lambda f x2 is less or equal to lambda times y1 plus 1 minus lambda times y2. So thus proving that the set E of f is convex. Proving that E of f is convex. So one part of the proof is done. Now let's take up the converse part. Conversely, assume that E of f is convex. Assume that E of f is convex. We will show that the function f is convex, and showing that f of f is convex, we need to show that f of lambda x1 plus 1 minus lambda x2 is less or equal to lambda f of x1 plus 1 minus lambda f of x2. Okay, so let's choose 2 points x1 and x2 in the interval I. Let x1 and x2 be 2 points in the interval I, in I. And let z1 be a point which is x1 defined as x1 f of x1, and suppose choose a point z2 which is defined as x2 f of x2. Now we can see that these 2 points z1 and z2 lie inside E of f. As we know, the definition of E of f is it contains those points x and y for which f of x is less or equal to y. So here we have the point x1 f of x1, but so therefore in place of x we have x1, and in place of y we have f of x1. But here f of x1, the image of this first point under f is f of x1, and it is equal to the second coordinate here. So therefore this point z1 belongs to E of f, and similar to the image of its x2 under f is f of x2, and so therefore the image of this x2 is equal to the second coordinate of this point z2. So therefore again this point z2 belongs to E of f. So then clearly, then by definition, both z1 and z2 are the points of E of f. Are the points of E of f. Now, by convexity of E of f, thus by convexity of E of f. By convexity, we need have that the line segment joining these 2 points lies entirely in E of f. So the point lambda z1 plus 1 minus lambda z2 also lies in E of f. Also lies in E of f, where lambda is a real number which varies in the interval 0 to 1. So now again, actually, this is not just a single point, but for every value of lambda, this lambda z1 plus 1 minus lambda z2 always lies in E of f. So actually for different values of lambda, and in fact for all the different values of lambda in the interval 0, 1, this notation lambda z1 plus 1 minus lambda z2 represents the locus of all the points on the line segment joining z1 and z2. So therefore this is just not a single point, but for different values of lambda, this represents the locus, this represents the, in fact, for all the values of lambda, this represents the line segment joining Z1 and Z2. So therefore, so when this point lies inside, when this point is inside the set E of f, then by definition of E of f, this point can also be written in the form lambda x1 plus 1 minus lambda x2, and the second coordinate is lambda f of x1 plus 1 minus lambda f of x2. So therefore, when this point is inside E of f, that ordered pair will also be in E of f. So thus we have lambda x1 plus 1 minus lambda x2, and here lambda f of x1 plus 1 minus lambda f of x2. This belongs to the set E of f. So this can clearly be obtained by putting the values z1 here, and in place of z1 we will write x1 f of x1, and in place of z2 we will write x2 f of x2. Then we will get this equation, and since this is inside E of f, so therefore this point is inside E of f, and this is true for all lambda belonging to the interval 0 to 1. So when this point is inside E of f, then we can employ the definition of E of f. So thus by definition of E of f, thus by definition of E of f, we have, now image of this point will be less or equal to this point. We have this f of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda times f of x1 plus 1 minus lambda times f of x2. So this completes the proof. Actually, this is the definition of a convex function. So thus, f is convex. Okay, so we have completed the proof of this result. So therefore, a function f will be convex if and only the set E of f associated with it is a convex subset of R square. So once we have done this theorem, now we will take up one more nice fact of how we will prove a given function to be convex. This is actually a test of convexity. So one nice test of convexity. Test of convexity. In fact, these are all the tests of convexity, but here this is one more useful test and it is more simpler. So a function f from I into R is convex if its second derivative is positive, if f double dash of x is greater or equal to 0 for all x belonging to the interval I. And in fact, this test can only be used provided that the second derivative exists for such a function. So this is one, and second one, a function f from I into R is concave if f double dash of x is less than or equal to 0 for all x belonging to the interval I. And in both of these cases, provided f double dash of x exists. So in fact, if this second derivative does not exist for a function at any point or at some point, then this test cannot be used. We must have a value, we must have this function f is differentiable at every point. And if we, after being differentiable at every point, if it happens that it is greater or equal to 0 for all the points inside I, the second derivative is greater or equal to 0 for all the points inside I, then such a function is convex. And if the second derivative is less or equal to 0 for all the points, then such a function is concave. And in fact, if this f double dash of x is greater or equal to or greater than 0, if this is greater than 0 for some x belonging to I, and f double dash of x is less than 0, or f double dash of x is f double dash of x dash is less than 0 for some x dash belonging to I, then f is neither convex nor concave. F is neither convex nor concave. And in fact, the last one is if f double dash of x is equal to 0 for all x belonging to I, then equal to 0 means it can be written as greater or equal to 0. It is also less or equal to 0. So therefore, when f double dash of x is equal to 0 for all x belonging to I, then f is both convex. F is both convex and concave. So this is the test of deciding whether a function is convex or concave. Now let's take some examples. And let's take the function f of x is equal to e power x on r. Then let's see whether this is a convex function or a concave function. So clearly, f of x is equal to e power x is twice differentiable. We just need it to be differentiable 2 times, twice differentiable. In fact, this is every derivative exists here. So, and f double dash of x is equal to e power x, and we know that this is greater or equal to 0 for all x belonging to R. So thus, f of x is convex. But in fact, we have that f of x is equal to f double dash of x equal to e power x. This in fact greater than 0 for every x belonging to R. So therefore, the function is convex. Now, similarly, example number 2. F of x is equal to log x. X greater than 0. So solution. Again here, clearly, f of x is twice differentiable. F of x is twice differentiable, and f double dash of x. Now the first derivative is 1 by x, and the second derivative is minus 1 by x squared. Now, since here this x is a real number, it's a positive real number. So when we have minus 1 by x squared, so therefore this quantity is always less or equal to 0 for all x belonging to R. Now here we have the condition that x is positive. So therefore this is less than 0 for all x greater than 0. So therefore f of x is concave. Thus f of x equal to log x is concave. And let's take one more example. Example number 3. F of x is equal to x power alpha on 0 to infinity. Now here alpha is any real number from alpha is any real number, and x belongs to 0 to infinity, x a positive real number. So this alpha here. Now we will see that whether this function is convex or concave. So in fact, this is the power, these are the powers of x. So therefore, this function is also clearly differentiable. So in the solution, clearly, f of x is differentiable. In fact, y is differentiable. Now let's take the second derivative, and f double dash of x, this is equal to alpha into alpha minus 1 into x power alpha minus 2. Now, since x is positive, so therefore, the positivity or negativity of the second derivative will completely depend on the real number alpha. It will not depend on, now since this x is positive, so x power alpha minus 2 is always positive. Therefore, the negativity and the positivity of this f double dash of x will completely depend on the point alpha. Okay, now we'll choose two cases. If alpha belongs to the interval 0, 1 and alpha is a different number. Okay, now, so if alpha is, suppose, greater or equal to 1. If alpha is greater or equal to 1, then alpha minus 1 is greater or equal to 0, and alpha into alpha minus 1 is greater or equal to 0. And so f double dash of x is greater or equal to 0, implying that f of x is convex. Implying f of x is convex. So when we have this alpha is greater or equal to 1, then alpha minus 1 will be greater or equal to 0. If you multiply these two equations, we will get alpha into alpha minus 1 is greater or equal to 0. So when alpha into alpha minus 1 is greater or equal to 0, x is always a positive number. So this x for alpha minus 2 is always greater or equal to 0. So that means f double dash of x is greater or equal to 0, meaning that the function f of x equal to x for alpha is convex. Now second, and if suppose 0 is less than alpha and less than 1. If 0 is less than alpha less than 1, so that means alpha is less than 1, then let us see what is alpha minus 1. Then alpha minus 1 is less than 0. And so alpha into alpha minus 1. Now this alpha is less than 1, but alpha is positive. So therefore this alpha is always positive, but alpha minus 1 is negative. So this product is less than 0. So in fact, we can take this is, suppose let's take 0 less or equal to alpha less than 1. Then we will get alpha minus 1 is less than 0. And alpha into alpha minus 1 is, suppose, less or equal to 0, implying f of x is concave. So therefore, on this domain, when alpha lies from 0 to less than 1, then this alpha into alpha minus 1 is less or equal to 0. So therefore, f double dash of x is less than or equal to 0, and so the function f of x is a concave function. And finally, finally, if alpha is less than 0, then alpha minus 1 is again less than 0. Because when we say, in fact, their alpha minus 1 will be less than minus 1. So therefore, this again less than 0. So thus, alpha into alpha minus 1. So when we multiply two negative quantities, we get this is greater or equal to 0. And so
it's 7 o'clock.
And so f of x is greater or equal to 0, implying f of x is convex. So therefore, what we can conclude finally is that the function f of x defined in this way x for alpha when x belongs to x is a positive real number, then this function is concave, provided alpha belongs to this interval 0 to less than 1, in fact closed on 0 and open on 1. Then in this case, this is the only case where the function f of x defined in this way is concave. So this is the case when this function is concave. And if alpha does not belong to this domain, then the function f of x defined in this way is always convex. So therefore, we will write the conclusion here. Conclusion, if alpha belongs to the interval 0 to 1, then f of x equal to x power alpha is concave. And if alpha belongs to, in fact, if alpha is equal to 0 also, then we also have the function in even convex. And so if alpha belongs to this R minus 0 to 1, it is the open interval 0 to 1, because when we put alpha equal to 0, then we will get this f of x equal to 1. So let me write this clearly that this is the open interval 0 to 1. So this is the open interval 0 to 1. Then f of x equal to x power alpha is convex. X power alpha is convex. So therefore, when alpha belongs to this domain, then it is a concave function, while x is a positive real number. And if alpha belongs to R minus open interval 0, 1, then it is a convex function. In fact, the point 0, alpha is 0 here, and alpha is also 0 here. So therefore, for alpha equal to 0, this function is both convex as well as concave, because for alpha equal to 0, this will become a constant function. And the second derivative of a constant function is 0. So such a function satisfies f double dash is greater or equal to 0, and it simultaneously satisfies f double dash of x is less or equal to 0. So therefore, the function will be both convex as well as concave. Well, so we have concluded this up to this stage, but let me write one more an example here. So this exercise number 4, f of x is equal to sine x on the interval 0 to pi. And similarly, we will write one more result here, or we will write a note. If f is convex, then minus f is concave. And in fact, the conversely also. If f is concave, then minus f is convex. Now, this is an example that you will try yourself. This is one more note that if f is convex, then minus f is concave. So with this, we conclude the today's lecture. And in the next lecture, we will do the Jensen's inequality.